The last thing that we're going to discuss in logarithms and exponents is logarithmic equations. So this is another case where we kind of learn by doing. And the thing to remember and to always remember is that the purpose of a logarithm is to solve for the exponent. And if you remember this, then actually solving most equations is going to be pretty straightforward. So let's learn by doing. We're going to take a bunch of examples. First example is 3 to the t is equal to 243. And what we're essentially saying here, and we've talked about this before, is that the log says what power of 3 will give us 243. So we can take this and put it into logarithmic form. So t is equal to log base 3 of 243. Now the problem is that in our calculators, most calculators, there is no log base 3. Okay, and if there is no log base 3, then how are we ever going to find this unless we're really familiar with the powers of 3? So we can do something else instead to solve. So this is to solve without needing base 3 in our calculators, because if you look in your calculator, you're going to see that they have log and they have ln, but they don't have a place for you to specify what base for log. Okay, you can see even in this calculator here, here's the log, that's indicative of log base 10, okay? Not any other base. So here, what we're going to do is we're going to start with 3 to the t is equal to 243. And we're going to take the log of both sides. We're doing it to both sides, so we're preserving the equality of 3 to the t and 243. So that's going to be our first step. Take the log of both sides. And then you can see here that this t is an exponent. So we can apply the power property. And we can say, okay, well now, this is t log of 3 is equal to log of 243. So notice what we did here. We can't solve when there's an exponent unless we use logs, because what logs will do is it'll take the variable out of the exponent. That's the whole purpose. Okay, so we're going to apply the power property. That's what we did here. And remember that these equations can only really use the 4 properties that exist. So that's why I say that even the most complex equations are pretty simplistic because we only have 4 properties to use. So this is the power property. That was log base b of m to the x is equal to x. Sorry, let me rewrite that. It was x to the m. I just want to be consistent. Log base b of x to the m becomes m log base b of x. That's the power property. Okay, so the next thing that we can do is solve for t. So solving for t is just isolating our variable. We can divide both sides by log base 3. So that means t is equal to log of 243 over log of 3. And if we go into our calculator, we have for a lot of calculators, including this one, in order to put in the log, you type in the number first, and then you do log. Okay, so log of 243 is 2.38, and then we're going to divide by and put it in parentheses log of 3. So put 3 first and then log, and then just close your parentheses. And you get 5. Okay, so in some calculators you could type log and then the number. In this one and in a lot of the others, you type the number and then log. And what do we get? We get that t is equal to 5. So again, what did we do? We isolated the variable. And notice our variable here is t. It's not x. And that's it. Okay, let's try another one. So our second example is 6 to the x is equal to 98. And unlike the previous one, some people might know their powers of 3 really well, and they might be able to figure out, oh, well, t is equal to 5, because 243 is a power of 3. That is not the case here with the 98. 98 is not a power of 6. So you are going to get a decimal answer, which means that you can't say, okay, well, 6 to the first, 6 to the second, 6 to the third. You can't sort of try it and do it by guess and check, okay? So let's do this again. So let's look at our rules. We're going to take the log of both sides. So that means that we're going to do log on the left and log on the right. So log of 6 to the x is equal to log of 98. So we took the log of both sides. Now we're going to apply the power property. Okay, so it's the same 3 rules. We're applying the power property. So we get x log of 6 is equal to log of 98. And then we isolate the variables. So same 3 rules. Take the log of both sides, use the power property to get the variable out of the exponent, and then isolate that variable. So we can divide both sides by log of 6. Which means x equals log of 98 over the log of 6. Practice putting this into your calculator. You should be getting 2.5 2.56. And I'll do that here. I won't do this all the time. Okay, in other words, a lot of times I'll just write down the answer. So log of 98 divided by the log of 6. And we get 2.56. Okay, same three rules here. Nothing changed. Okay, let's go to another one. A little bit different this time. It's the same three rules. It's just that I'm going to add one thing. I'm going to add an extra constant on one side. So 2 times 8 to the n is equal to 942. Okay, when you see this, only the 8 is being raised to the m power. You cannot take the log of both sides at this point, because that's going to make things more complicated. Because then not only will you be using the power rule, but you can't move this variable out to the front, okay? You can't move the variable out to the front because the m only applies to the 8 if you take the log of both sides at this point. You also, order of operations, you cannot multiply the 2 and the 8. This is not equal to 16m. So I'm going to put these two things as a note on the side, just off to the side here, okay? So the first thing is 2 times 8 to the m is not equal to 16 to the m. Order of operations, the 8 needs to be raised to the m first. Okay, second thing. Only the 8 is raised to the m power. What this means is log of 2 times 8 to the m is not equal to m times the log of 2 times 8. Because you can only bring the m out to the front if it applies to everything. What it is equal to, and I'm writing this down because I want you to understand the properties of logs. This is equal to log of 2 plus log of 8 to the m. Okay, the thing is that because of all of this, the first thing that we want to do here is actually isolate our exponential function and then take the log of both sides, okay? So in order to isolate our exponential function, we're going to divide both sides by 2. So that's our first step here. And what that will give us, sorry about that, is 8 to the m is equal to 471. And now we can proceed like we had in the past. We're going to take the log of both sides, because now it looks just like these, right? We have something raised to a power is equal to a constant. So we use these three rules. Take the log of both sides, power property, isolate the variable. Nothing changed. So we're going to take the log of both sides. On the left, we have log of 8 to the m. And on the right, we have log of 471. Then we're going to use the power property. Power property says move the exponent out to the front, so we get m log 8 is equal to log of 471. And again, notice what this does. It takes the exponent out of the exponent. And then finally, we can isolate the variable by dividing both sides by the log of 8. Isolate the variable. And that's going to give us m is equal to log of 471 over log of 8. Plug it into your calculator. You will get 2.96. Okay, now what all of this does, so we're going to pause. What all of this does is it tells us how to convert from one base to another. Because if we go back here, what you saw is that t itself is in base 3. But now, right, t is log base 3. But now we have a log base 10. And what that does is it allows us to put it into the calculator. Here we couldn't, here we can. So if you're ever given a log that's in a different base, we can put it into base 10 so that it is something that we can put into the calculator. And the way that we would do that is exactly what we do here, where we take the log of both sides and then we isolate the variable, okay? So let's just write this down. This is how we convert between bases. So let's take y equals b to the x. Sorry, I don't know why I said that. We want logs. Y equals log base b of x. Okay, so how do we convert to base 10? And by the way, converting to base 10 is exactly the same as converting to base 12, base 200, or base e, whatever base we want. Okay, so we convert it to an exponential function. That's the first thing that we can do. B to the y is equal to x. Then exactly what we've done. We're going to follow these 3 rules. Those 3 steps. First thing, take the log of both sides. So log of b to the y is equal to log of x. Then we're going to take that y and we're going to move it out to the front. This is the power property. And we get y times the log of b is equal to the log of x. So we use the power property, and now that last step is to isolate the variable. So we want y, right? We want to know what this is. So we want to solve for y. That's our variable here. So we divide both sides by the log of b. So what we're saying here is y is equal to log x over log b. Or we don't even have to say y. We can say log base b of x is the same thing as log x over log b. And actually, we didn't have to take base 10 of both sides. We could have taken base 12 of both sides. So this is what we're really looking for, because a calculator can plug in base 10. A calculator can also plug in base e. You see on this calculator, it has a ln. So we could use ln instead of log. So if we use base e, in this step, instead of taking the log of both sides, we would take the ln of both sides. And everything would be the same, except at the end, we would have ln x over ln b. Or we could take any base. Could be base 12, it could be base 25, it doesn't matter. Let me make that a little bit clearer. Okay, so let's summarize. You first convert to exponential form. Then you take the log of both sides. You can also take log base a of both sides or ln of both sides to convert to other bases. Now, you may say, well, when would we do this? Ln will come to, okay? In terms of other bases, our world works in base 10, okay? 10 fingers, 10 toes. But if you take, let's say, the computer world is base 2 or base 16. We use hexadecimals too in computers. So it could be base 16. You could have in other worlds, in other systems, we might use different bases, and that's when you might be converting to other bases, okay? And then your last step, then you do the power property, just like before. And then you're isolating your variable. And in this case, your variable is whatever your exponent was. And now that you know how to convert between bases, you don't have to go through this whole long process each time. You can just automatically, okay, convert. So in other words, log base 6 of 11 is equal to log of 11 over log of 6. You don't have to go through this whole process. You can just, do the conversion. Log base 8 of 15 can also be written as ln of 15 over ln of 8. Or it could be written as log of 15 over log of 8. That's fine also. So it just depends on what base you want. Okay, so now that we did this, okay, you know how to convert between bases. You can take something like log base 3 of 243 and put it into a calculator. Let's move on. Let's do some more equations. And some of these are going to look more exponential than logarithmic, like this next one. So we have 3 to the x minus 2 is equal to 3 to the 2x plus 3. I'm going to remind you that as soon as you think you've gotten the hang of it, pause the video, solve it on your own, and then restart the video and make sure that you're getting the right answer. So in this case, the bases are the same. And if the bases are the same, then the exponents have to be the same. You can't have 3 to the 5th is equal to 3 to the 6th. That doesn't make sense. So we could just set the exponents equal to each other. We are not doing any division. Notice I'm not dividing both sides by 3. You can't do that. I'm going to change this to red so that you can easily see what's the solution and what's the problem. Okay, you can't divide by base. You can't divide both things by 3 because what that's going to do is it's just going to leave the exponents sort of hanging in the air. The exponents are attached to the 3, so you can't take away the 3. The exponents can't just fall down, okay? What we're doing is we're saying if the bases are the same, the exponents are the same. Now what that means is that we just have a linear equation. So we can subtract x from both sides and subtract 3 from both sides. Okay, you can do this in one step. You can do it in 2 steps. I'm just doing it in one for timing purposes. We get -2 minus 3 is -5, and 2x minus x is x. So x is equal to -5, and this is our answer. Okay, simple enough. Okay, let's complicate it just a little bit. Let's say instead of having the same base, we have 2 to the 3x is equal to 8 to the 2x plus 1. Okay, we have 2 methods here. Both methods work. The second method works all the time. The first method will not. So in the first method, what we're going to do is we're going to express both sides as the same base so that essentially we can do what we did here. We could say you have the same base, the exponents must be the same. The reason why I say that that doesn't always work is that sometimes the bases can't be expressed as the same base. It's just not possible. So in this example, they can be. we will do examples where you have to use method 2. Okay, so method 1. Only works when we can express both sides with the same base. Okay, here we can do that. 8 is equal to 2 to the third. So what does that mean? We have 2 to the 3x is equal to, and now we have 2 to the third to the 2x plus 1. So we did a substitution. Now the next thing that we're going to do is we're going to get rid of the parentheses. By distributing the exponent. So we know that an exponent raised to an exponent, we can multiply. So that means that we have 2 to the 3x, and this becomes 2 to the 6x plus 3. So we just distributed this 3, multiplying it. And then we could say, again, well, the bases are the same, so the exponents are the same. And what does that mean? That means that then we can just solve for x. So here we're saying we have a base 2 on both sides. So 3x is equal to 6x plus 3. To solve, we get the x's on one side, the constants on the other. So we subtract 6x from both sides. We get negative 3x equals 3. And we can just divide both sides by negative 3. So x equals negative 1. Okay, method 2. In method 2, again, this always works. You're going to take the log of both sides. Which means we're going to take the log on the left. We're going to take the log on the right. So we have log of 2 to the 3x is equal to log of 8 to the 2x plus 1. Now we apply the power property, just like before. So when we apply the power property, we have 3x times the log of 2 is equal to, and it's really important, this has to go in parentheses. Otherwise, it looks like you're only multiplying the log by 1 as opposed to 2x plus 1. Okay, so let's just make a couple of notes here. You take the log of both sides. Then you're going to use the power property. Make sure that when you move the exponents out to the front, you put them in parentheses. If you forget to do this, it's not that you'll get the wrong answer, because most likely you won't. Okay, students don't get the wrong answer, but you are writing it incorrectly, so it is incorrect. Your work is based on incorrect stuff, because if you don't put parentheses and you continue to work, then the problem is that you're going to multiply log 8 by 2x plus 1 when your work says, without parentheses, log 8 should only be multiplied by 1. Okay? Now, when you look on the internet, a lot of things on the internet, what they will do is they'll distribute the log 8 now, and if it were necessary, the log 2. And then they'll work with all of that stuff to get a long, complicated expression. You can do that. You can look online. I'm not going to do that here. I'm going to try and simplify it as much as possible. Because working with all of those extra letters in there, they make things confusing sometimes because it's just so much stuff to think about. If you're okay with that, that's fine, okay? If you are not okay with that, then keep following this. So once we move the exponents, what we're going to do is we're going to divide one of the sides by divide both sides by one of the logs. It doesn't matter which side. Okay, I tend to prefer dividing by things that I know are going to be easy to multiply by. So I see a 1 here, so that's easy to multiply. So I'm going to divide both sides by log of 2. But you could divide both sides by log 8. It doesn't matter. I just wrote log 8, but I meant log 2. That means that will go away. And log 8 over log 2, when you put that into your calculator, you just get 3. So you're going to get 3x is equal to 2x plus 1 times 3. Or 3x is equal to 6x plus 3. And at this point, I'm not even going to go through the solving because we've done this. We did this up at the top. And we got that x is equal to -1. Okay, so we solved it up above. And essentially what we did is once we divided by the logs, we distributed. And then we solved the linear equation. Okay, let's take another example. We're going to do just a few more examples. And in the first one, we are able to express as the same base, so we will do that. And in the remaining two that we do, we will not be able to express as the same base. So we'll have to use method 2. Okay, so in example 3, we could use either method, whereas in examples 4 and 5, we can only use one. Expressing as the same base is much easier. At least in my opinion. I think it's much easier. So we have 9 to the 6x plus 1 is equal to 27 to the 8x minus 2. So these can both be expressed using base 3. Remember, we're thinking of powers. So most common mistake is people will say that 27 is 9 times 3. That doesn't work, okay? So they're both powers of 3. So just as a note here, 9 is equal to 3 squared. And 27 is equal to 3 cubed. So if that's the case, we can replace 9 with 3 squared. And 3 squared is raised to the 6x plus 1. And we can replace 27 with 3 cubed. 3 cubed is raised to the 8x minus 2. So we're expressing as the same base. Then we're distributing the exponents. So we get 3 to the 12x plus 2 is equal to 3 to the 24x minus 6. The exponents are equal because the bases are equal. So 12x plus 2 is equal to 24x minus 6. And now it's just a matter of solving our linear equation. So you can subtract 12x from both sides and add 6 to both sides. That will give us 8 is equal to 12x. Divide both sides by 12. X is equal to 8 over 12, which is equal to 2/3. Reduce your fractions. Always reduce. Okay, just to summarize what we did here. We use substitution to make the bases the same. Distributed the exponent. We set the exponents equal to each other. Because the bases are equal to each other. And then we solve the linear equation. Okay, let's do another one. So this time, 4 to the 2x minus 1 is equal to 6 to the 4x minus 3. They cannot be expressed as the same base. So you have no choice. You must use method 2. So you're going to take the log of both sides. So we're going to take the log on the left and the log on the right. We move the exponents out to the front, put it in parentheses. 2x minus 1 log of 4 is equal to 4x minus 3 log of 6. Then we divide both sides by one of the logs. So it doesn't matter which side you do. You'll get the same answer in the end. It's just that the next step will have slightly different numbers. But then when you go through and you solve everything, you'll get the same answer. So I'm going to choose to divide both sides by log of 6 because I'm going to get a decimal. And it's so much simpler just to multiply that decimal by 1 than it is by, let's say, 3. Okay? But that's the only reason. It's personal preference. So we divide both sides by log of 6. Goes away on this side. Divide this side by log of 6. And log of 4 over log 6 is equal to 0.77. Okay, is equal to 4x minus 3. 0.77 is log 4 over log 6. So let's just quickly summarize what we've done so far. We took the log of both sides. Divide both sides by one of the logs. And we found that log 4 over log 6 is equal to 0.77. So our next step is to distribute and solve the linear equation. Now again, online, in some cases, you'll find that you'll get 4x log 6 minus 3 log 6 on this side. They'll tell you to distribute the log 4, and they'll say 2x log 4 minus log 4. And then they'll have you solve for x that way by adding log 4 to both sides and then subtracting 2x log 6 from both sides. And then you'll get some complicated expression, and it's not worth it, in my opinion. And at the very end, you have to put it into your calculator. You must get a linear answer at the end, okay? You can't end with some complicated expression. That doesn't help us. We need something, a number, okay? So we're going to distribute the 0.77. This gives us 1.54x minus 0.77 is equal to 4x minus 3. And then we're just solving. So we can subtract 1.54 from both sides, 1.54x. Add 3 to both sides. So that the 3's cancel on one side, the 1.54x's cancel on the other side. I'm not spending a lot of time on this because we went over solving linear equations in the first unit. So you can go back to those videos if you have questions. We have 2.23 is equal to 2.46x. Divide both sides by 2.46. And you get that x is equal to 0.191. This is your answer. It is a decimal answer. You cannot express your answer with logs. Not in my class. I want to know that you are able to get an actual answer. So in my class, you can't have an expression with logs and say that's your final answer. Okay? Let's do one more. So in the last one that we do, we have e to the 2x minus 3 is equal to 5 to the 3x minus 4. So again, can't be expressed with the same base. So we have to use method 2. So in this case, we've been using base 10. But in this case, it actually makes sense, instead of taking the log of both sides, to take the ln of both sides. The reason for that is that the ln of e is equal to 1. Okay? So take the ln of both sides because the ln of e equals 1. How do we know that? Log base e of e equals 1. Log base a of a is equal to 1. If the base is the same as the argument, then the log is 1. Okay? This is like saying a to what power is equal to a? And that what power is 1, right? A to the first power is equal to a. Then everything else that we do is exactly the same, except you don't need to divide both sides. you're going to wind up, you'll see, finding the ln of 5. And then we're just rewriting the steps from the other side. You're distributing and you're solving for x. Okay, what does this look like? You take the ln on the left and on the right. You get ln of e to the 2x minus 3 is equal to ln of 5 to the 3x minus 4. 2x minus 3 comes out to the front in parentheses, times the ln of e is equal to 3x minus 4 comes out to the front, times the ln of 5. And the ln of e is just 1. So we can just ignore that. Anything times 1 is itself. The ln of 5 is 1.61. So we could just say 2x minus 3 is equal to 1.61 times 3x minus 4. That's a parenthesis. And then we distribute this 1.61. So when we distribute the 1.61, we get 2x minus 3 is equal to 4.83x minus 6.44. Isolate. So we can subtract 2x from both sides and add 6.44 to both sides. $6.44 will cancel, the 2x will cancel, and you will get 3.44 is equal to 2.83x. Divide both sides by 2.83. And you get that x is equal to 1.22. So these expressions are logarithmic, but they're also in some ways exponential. Okay, in our next video, we're going to be talking about equations, all of which we start off with logs in them.